So this is the review for the Fall B Stats course. This is for Test 2, which is Chapter 3. Trying to make that a little more flat there. I will be emailing the link to the recording to everyone. And if you need to reach me directly, my email address is here, but you can also email me at maxine.horn@daytonastate.edu. All right, so let's dive in here. We've got, I think, 28 questions that we're going to get through today. So we're going to go through how to do some of these by hand, but we are, when we can use the calculator, I'm going to show you how to use the calculator, because they're not expecting you, unless they say specifically that they want you to use the formula, they're not expecting that you use a formula when you could instead use the calculator. So I'll point that out when we get to those problems. All right, so number 1, use the fundamental counting principle to solve the problem. How many different codes of 4 digits are possible if the first digit must be 3, 4, or 5, and if the code may not end in 0? So what you're going to do for this type of problem, here, I tweak this a little bit, is, my wires out of the way here. So they said that there's going to be 4 digits. So I'm going to draw 1, 2, 3, 4. This represents the number of options I have for my first digit are going to go here, second, third, and fourth. So I'm going to fill these in with the number of options that I have available for each of those, and then we're going to multiply these together. Now, when you're looking at how many digits you can put in, remember that you have 10 digits to choose from, okay? Because 0 is a digit. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which all together is 10 digits to choose from, okay? Some people forget about 0, but you can use 0, so you do have 10 digits to choose from. Okay, so what we're going to do first, or what I like to do first, is we're going to deal with the specific constraints that they gave us. The first digit must be a 3, a 4, or a 5. A 3, a 4, or a 5. So that's only 3 numbers that I can choose from for the first one. So that's what I'm putting in there. Then they say the code cannot end in 0. So instead of having all of these to choose from, I'm saying, no, I can't choose that one. I can only choose these. So instead of having 10 options, I only have 9 options for my last digit. But they didn't give me any constraints on my second or third digit. So I can put in a 10 for both of those. And so I'm going to plug that into the calculator. I'm going to say 3 times 10 times 10 times 9. So that gives me 2,700 or 2,700 different codes that I can make with those particular restraints. Okay. And that's the fundamental counting principle, where you say, okay, how many options do I have for each of these? And you multiply them together. Okay. Number 2, again, use the fundamental counting principle to solve the problem. Singer-songwriter wishes to compose a melody. Each note in the melody must be one of the 12 notes. We have 12 options, 12 notes in her vocal range. How many different sequences of 3 notes are possible? So very similar problem. I'm going to create a 3-note melody. This is my first note, this is my second note, and this is my third note. And I have 12 notes to choose from for each of these. They didn't say that we couldn't repeat any of them, or that, you know, it had to start with one particular note. So there's no constraints. So I can use all 12 notes for every single blank space that I'm filling in. So I can do 12 times 12 times 12. Or if you wanted to, and I just want to make sure that I can show you this on the calculator, if you're doing a number a ton of times, here it was only 3 times, but let's say we were doing this, I don't know, 47 times or something ridiculous. You can take your number to a power. This little caret symbol is how you can do that. So if I wanted to write this as 12 to the third, because I'm multiplying it by itself 3 times, I would go 12, and then you hit the caret button, and then it creates the exponent there, and then you hit 3. To get out of the exponent, if you need to, like if you're going to do something after that, you hit the right arrow for it to get out of the exponent. And it's going to give you the same number either way. Okay. All right. So same general process for that one. Okay, if an individual is selected at random, what's the probability that he or she has a birthday in July, and then ignore leap years? Okay, so when we're looking at probabilities like this, and just kind of in general, when you're looking at probabilities, it's often helpful to think of it as kind of like the part over the whole. So like, what is it that I'm looking for out of what are my total options? So for this, we're going to say, well, my numerator needs to be the number of days in July out of all of the days in the year, the total number of days in the year. Okay, so there are 31 days in July, and ignoring leap years, there's 365 days in a year. Now, sometimes, like in this problem, they might just have the answer as a fraction, and so you would just leave your answer as a fraction. Sometimes they're going to have your answer as a decimal, in which case you would take this and you would just plug it into the calculator, and then you would round to how many ever digits they tell you to round to. So as like a test taking strategy and like a time saving thing, before you like get into a habit of taking your fraction and plugging it in to get a decimal, just do a quick check of what your answers look like, what your potential answers look like, so that you don't do an extra step that you don't need to do. So we would just leave this as a fraction, 31 over 365. Okay, the distribution of blood types for 100 Americans is listed in the table. If one donor is selected at random, find the probability of selecting a person with blood type A positive or A negative. Okay, so let's talk about that or. So when you have the word or, that tells you that you're going to be doing the addition rule. Okay, now the addition rule says that you're going to do the probability of A. Well, so that's the probability of A or B. Okay, so is equal to the probability of A plus the probability of B minus anywhere where they overlap. So the probability of A and B. So you're going to say, well, if I want the probability of this or this, I'm going to add the probability of one of those things plus the probability of the other thing, but then I need to make sure that I subtract anywhere that they overlap if they do overlap. Because if they do overlap, then I've counted that area twice because I counted it for this one and this one. Now, sometimes there's not going to be an overlap. Like in this problem, there isn't an overlap, but it doesn't change the formula. This is still the formula when you have the or, right? So the or, that tells you this is the addition rule. The or is one, then the other, then subtract where they overlap so you're not counting that part twice. Okay, so let's actually do this one. So we want the probability. So first of all, they said 100 Americans. That is our total number. That's like our that's our n value. That's going to be our denominator. I think they've talked about n like the total number that you have available. So this is going to be our denominator. This is how many people there were to choose from. There were 100 people to choose from. So we're going to create a fraction for the probability that somebody has A positive blood. We're going to add to that a fraction representing the probability that somebody has A negative blood. And if there were a way to have both A positive and A negative blood, we would subtract that. But there isn't. You're either one or the other. There is no overlap. There is no and. So we're just gonna do this part and this part because this part doesn't exist in this problem. Okay, so those denominators are going to be 100 because that's how many people there were. Now, that's nice that they told us that there were 100 Americans, but they didn't have to. If they didn't tell us that, what we would have to do is we would have to add all of these up, right? So using some of the symbols that we learned in the last chapter, we would have like the the sum of the frequencies, right? And we would do 37 plus 6 plus 34 plus 6 plus 10 plus 2 plus 4 plus 1, and that would give us 100, and that's how we would know what our denominator would be. So they're not always going to give you that. You might have to find it yourself, but they gave it to us, so we're going to use it. Okay, so then we need A positive. So out of those 100 people, how many of them had A positive blood? 34. So the probability that somebody has A positive blood is 34 out of 100. Same thing with the A negative, right? We're just looking at, well, how many were had the A negative blood. Okay, so before I deal with these fractions, I take a look at my answer and I see they have these as decimals rather than fractions. Now, there's a couple ways you could do this. You could just go ahead and add these together. They already have a common denominator, so we're allowed to keep the denominator and add across the top. Okay, so sometimes in stats you end up doing a little bit of algebra refresh, like how to add and subtract fractions. You do need to have a common denominator to do that. Or if you don't want to think about that, you just plug it into your calculator and you say 34 out of 100 plus 6 out of 100, and it's going to give you your decimal answer. Or you could do the fraction and then you could say, okay, well, what's 40 out of 100? Or maybe you get to here and you realize, oh, right, that's out of 100. So that's just 0.4. But however you do it, you end up with the answer of 0.4. Okay. All right. Number 5, the distribution of master's degrees conferred by a university is listed in the table. And then we've got some majors and their frequencies. What is the probability that a randomly selected student graduating with a master's degree has a major of engineering? Round your answer to 3 decimal places. Okay, so we were just talking about, if they don't give you the total frequency, you have to find it yourself. Let's go ahead and do that. We got to add all of these up, right? So if there's not really a ton of room here, but the sum of the frequencies equals, just for the purposes of time, I'm not going to plug this into the calculator, but trust me, I did this problem before, and if I add all of those up, you get 888. So the total frequency is 888. So our denominator is how many people there were total. Our numerator is how many of them majored in engineering. That's 67. So again, that's the number of engineering degrees, people who majored in engineering, over the number of all degrees, or master's degrees specifically, right? So we plug that into the calculator, 67 over 888, and we get this decimal. So quick reminder about rounding, 0.07545045005. Okay, they want us to round to 3 decimal places. So I'm going to say 1, 2, 3. I'm going to underline that number. I look to the number to the right. If that's supposed to be an arrow. If that number is 5 or more, then my underlined number goes up 1. If that number is not 5 or more, my underlined number stays the same and everything else disappears. This is not 5 or more, so this is going to stay the same. So that's why this turns into 0.75. Again, as I always say, make sure you've got all these little things correct, like rounding correctly and plugging into the calculator correctly. You don't want to get a question wrong because you made a little mistake as opposed to, because you don't understand how to do the problem. Right? It's always frustrating when you do actually understand how to do the problem and you just make a little mistake that gets you the wrong answer. So take your time, double check yourself, make sure everything makes sense. All right. Explain why the statement is incorrect. The probability of rain tomorrow is 136%. Okay, so when we talk about probabilities, so there's a bunch of ways to think about it, but probabilities are always going to be between 0 and 1 inclusive, right? So you might see it written like this, where the probability of an event is less than or equal to 1, and it's greater than or equal to 0. If the probability of something is 1, it is certain that it's going to happen. Okay, if the probability is 0, that means it's never going to happen or it's impossible. Okay, so like if I look outside and I see that it's raining, I can say the probability of it raining today in my area is 100%, or is 1 if I'm giving it as a decimal, because I'm certain that it's going to rain because it's already raining. If I said, the probability that my birthday will be in February is 0. Well, my birthday's in October, so it's never going to happen that my birthday will be in February. It's impossible for that to happen, so I can say that it's 0. What I can't be is 136% sure of something. I can only be between 0 and 1 inclusive. Inclusive meaning that I can include the boundary numbers of 0 and 1. So what's wrong with that statement? The probability of an event cannot exceed 100. It can only be between 0 and 1. All right, the probability that an event will happen is, and they give P of E, probability of E equals 0.44. Find the probability that the event will not happen. Okay, so that's called the complement. Complement, I think I spelled that correctly. So the probability that something will happen, if you subtract it from 1, you're going to get the probability that it will happen, because the complement of something is what will add to it to be 1. So either it happens or it doesn't. So to find the complement, you're going to do 1 minus the probability of E. So in this case, they told us that it was 0.44. So if I do 1 minus that, I have 0.56. So thinking of it like, yeah, just either it's going to happen or it's not going to happen. But altogether, those two things need to add up to 100% or 1. I don't know that they're using this notation, but if you see it, you might see like, if I remember correctly, they have it where they put kind of like an apostrophe, but you have your event, the probability of the event plus the complement of the event is going to be equal to 1. So the thing plus the thing's complement is always going to equal 100%, or 1 if you're writing it as a decimal. Okay. Right, the frequency distribution, y'all should be familiar with that, right? You did that all for the last test. To the right shows the number of voters in millions according to age. Consider the event below. Can it be considered unusual? A voter chosen at random is between 35 and 44 years old. So first of all, let's talk about things being usual or unusual, okay? So we talked already about how we go from 0 to 1 with probabilities. So right in the middle then would be 0.5, right? 50% chance. So the closer you get to 0, the more unusual something is. The closer you get to 1, the more common something is, right? Because we talked about if it's at 1, it's certain it's going to happen. If it's at 0, it's never going to happen, or it's impossible, however you want to think of that. So as you head towards 1, it's common. As you head towards 0, it's unusual. So there is a cutoff that has been established about when we use the word specifically unusual, if something is or is not unusual. So that cutoff is that if the probability of an event is less than or equal to 5% or 0.05, the event is unusual. So if there's a 10% chance of something happening, we don't call that unusual. I mean, it's farther towards 0 than it is towards 1, but it's not unusual. But if it's 5%, we do consider that unusual. So unusual has a specific meaning, a specific numerical meaning in probability. So what we're going to have to do is we're going to have to find the probability that a voter chosen at random is between 35 and 44 years old and say, okay, is that less than or equal to 5%? If so, then yes, it's unusual. If not, then no, it's not unusual. Okay, so yet again, they haven't given us the sum of the frequencies. So let's go ahead and add those together to get the sum of the frequencies. And again, just for time purposes, trust me that it's 148.4, or don't trust me, plug it in yourself and verify to yourself, right? Trust but verify that it is 148.4. So that's our N, right? Sample size. That's the number of people that were in this survey. That's our denominator, is 148.4. Our numerator is going to be the people that are between 35 and 44 years old. So that's this class right here, the 35 to 44. So we have 26.9. So that's going to be our numerator, right? The numerator is the number of people that were between 35 and 44 years old. The denominator is the total frequency, the total number of people. Okay, so when we plug that into the calculator, 26.9 over 148.4, we're getting, and I'm going to round this to a few decimals. This is 181. Let's go to 3 decimals. It's about 0.181, which if I write it as a percentage, that's 18.1%. So 18.1%, it's definitely to the left of 50%, but it's not less than 5%, right? 18 is not less than 5. So no, the probability of the event is not close enough to 0. It's not this 0.05, which is what our cutoff is. Okay. All right, classify the events as dependent or independent. Okay, so we're going to talk about what that means in a minute, but let's read what the events are. Event A, a red candy is selected from a package with 30 colored candies and eaten. And then event B, a blue candy is selected from the same package and eaten. Okay, so when you're looking at independent versus dependent, for some of you, this might just be intuitive. You might look at this and you might be able to just immediately know. But if, and I'm going to write this out, if not intuitive, then fall back on the rule. Okay, so the rule is that if the probability of B, so you've got event A and event B, if the probability of B is equal to the probability of B given A, right? We read this as, that's given, right? If the probability of B equals the probability of B given A, then the events are independent. Okay. But if the probability of B is not equal to the probability of B given A, then they are dependent. Okay, so let's kind of walk through that here. Okay, so they didn't give us numbers for like how many red candies there were and how many blue candies there were. Let's go ahead and make up some numbers so we can actually do this as an actual example. Let's say that there's 20 red candies and 10 blue candies. Okay, so if I have, so let's forget about event A. Let's just find what is event B. A blue candy is selected from a package and eaten from this package that has 30 candies. Okay, so how many candies are there? There's 30. That's my denominator. How many of them are blue? We assigned the number 10. Okay, so if I plug that in, so this is the probability of B. This is the probability of event B, which if I plug that into the calculator, I get 0.3 repeating. I'm just going to go to 3 decimals. Okay, so that's just the probability of B. That's completely ignoring A. Well, now let's look at what's the probability of B given A. So given A means let A happen first and then see if that affects B. So if I have a bag of 30 candies, 20 of them are red, I specifically pull out a red candy and I eat it. When I then go to pull out a blue candy, what is my denominator? it's no longer 30. I don't have 30 candies in there anymore because I already ate one. I only have 29, right? So the act of doing event A changed what my denominator is for event B. I still have 10 blue candies, right? I didn't pull a blue candy. I still have 10 blue candies, but I don't have as many candies to pull from. I don't have 30 candies. I have 29 candies. So 10 out of 29, that's a different number. That's approximately 0.345, right? So that means that the probability of B and the probability of B given A, those two things are not equal to each other. And remember, the rule is that if they're not equal to each other, then these are dependent, right? What happens in B is dependent on what happened in A, right? So like I said, if you look at this and it's just intuitive to you, that's awesome, fantastic, your life is easy. If it's not, that's totally okay. Just fall back on your rule, okay? And maybe after a few times of doing this rule and proving to yourself what's happening in these different scenarios, you'll you might come to find that you can look at the problems and you can just kind of know what they're going to be, okay? All right. Okay, number 10, a group of students were asked if they carry a credit card. The responses are listed in the table. If a student is selected at random, find the probability that he or she owns a credit card given that they are a these freaking pencils, that they are a sophomore. Okay, so when you have that given, that tells you what your denominator is going to be. That's telling you, hey, don't look at everybody. Don't look at this total. We're not looking at everybody. We're only looking at these people. We're only looking at these sophomores. So when you see the given, that tells you the given, we're going to say, becomes the new sample space, right? It becomes the new n, the new denominator. Denominator. Okay, so what we're going to have here is we're going to have the denominator is the total number of sophomores. Okay, all right, so this first part, find the probability that he or she owns a credit card. It's not just the number of people that own a credit card that goes on top here. I have to have specifically the number of credit card holding sophomores, because I'm not allowed to look at anybody else. I'm not allowed to look at the freshmen. I'm only allowed to look at the sophomores. So I have to see, where does this overlap with what I was given? Okay, so a kind of easier way to do that is to go back to the chart itself and say, here, let me get my highlighter, and say, my sample space is sophomores. I'm only allowed to look at sophomores. We're looking for owns a credit card. So that's these, owns a credit card. But I'm only allowed to look at the things that I've highlighted in yellow. So I can only use 34. So my denominator is going to be the thing that I was given, is the total number of sophomores, which was 40. My numerator is where the thing that they're asking about intersects with the only thing I'm allowed to look at. So 34 out of 40. Okay. Then we go to plug that. Ooh, hold on. I just clicked out of this. Come on, maximize. No. Okay, sorry about that. Okay, so yeah, so we are just going to plug this into the calculator, 34 out of 40. So we get 0.85, and they want us to go to 3 decimal places. Don't forget that even though it's not written, there's actually an infinite number of zeros to the right of that. So just stick 1 0 on the end because they want a total of 3 numbers. So that's how they're getting 0.850. Okay, so remember, when they say given, that's the thing that comes after that, the thing that is the given, that becomes your new sample space. That becomes your new denominator. Okay. All right. Number 11, what is the difference between independent and dependent events? So we talked about this a little bit, but it's just putting this in words. Two events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. Two events are dependent when the occurrence of one event affects the probability of the occurrence of the other event. So the dependent example that we had previously was that when the occurrence of one event, pulling a red candy, affects the probability of the occurrence of the other event, pulling a blue candy from what's left in the bag. Okay. So it's just putting into words what we've already done in a problem. Right, number 12. So they're having us do like kind of two problems, but with the similar sets of numbers. So, or no, I'm sorry, they only gave us one survey results. I forgot that I created this twice so that we could work both problems out. So the accompanying table shows the results of a survey in which 250 male and 250 female workers ages 25 to 64 were asked if they contribute to a retirement savings plan at work. Complete parts A and B below. All right, find the probability that a randomly selected worker contributes to a retirement savings plan at work, given that the worker is male. Okay, so I have a given, I have this part of it, and I have this part of it. The given is my denominator. Okay, so what's given? That the worker is male. So we're going to do the same thing we did before, where we're going to say, okay, that's my new sample space. I'm no longer looking at the entire table. I'm only allowed to look at this row. Sometimes they'll give you something that's a row. Sometimes they'll give you something that's a column. In this case, they gave us something that was a row. So I'm only allowed to look at the male participants of this survey. So my new sample space, my new denominator is 250 because the given determines what my denominator is. Now for the numerator, we want to look at the people who contribute to a retirement savings plan, but I can only use the number that's highlighted. That's part of my new sample space, because remember, I can't use the rest of this. I can only use the highlighted part. So we have people who contribute and people who don't contribute, but again, I can only use the people who contribute that are male because male is the new sample space. Okay, so again, let's plug that into the calculator. 118 over 250, and that's how they're getting the 0.472. Okay, so B, find the probability that a randomly selected worker is female, given that the worker contributes to a retirement savings plan. Okay, so our given is our new denominator, our new sample space, and the thing that we're going to highlight, and the only thing we're going to be allowed to look at. What is the given? They contribute to retirement savings plan. So in this instance, our given is a column instead of a row. So the total number of people who contribute is 268. And then they want us to look at what's the probability that of those who contribute, somebody is a female. So here's circling the females, but again, I'm only allowed to look at where those two overlap. That's my numerator. Okay. Plug that into the calculator. And we get this number, which we already talked about rounding. If you take this and you go to round it, you're going to get 0.560. Actually, let's talk about that rounding because it's slightly more involved than the last rounding that we did. So they're rounding to 3 decimal places. You underline the place that you're rounding to. You look to the right. If this number is 5 or more, this goes up 1. If this is not 5 or more, this stays the same. This is 5 or more, so this goes up 1, but this is already 9. So for this to go up 1, it would need to become 10. Think of it as like 59 is getting rounded up to 60. So you actually have to change this 5 to a 6 and then that becomes a 0. Okay. All right. For the given pair of events, classify the two events as independent or dependent. Flipping a fair coin and getting tails, or flipping the same coin again and getting heads. Okay, so you need to always remember that a coin is an inanimate object, right? So is a dice, pair of dice, whatever you have. Cards, they're inanimate. They don't have memories, okay? They don't know that, oh, I'm supposed to be giving you heads half the time and tails half the time. They don't know that, right? Now, if you flip a coin a million times, you're going to get really close to 50-50 of getting heads and getting tails. But if you just flip a coin 2 or 3 times, you might get tails every single time. The coin doesn't know what it's quote unquote supposed to be doing. It has no memory. So flipping the coin has no bearing on what happens the next time you flip the coin. Now, if you do that a million times, like I said, you're going to get closer and closer to having 50% of one and the other, but doing it once doesn't affect what happens the next time. This event is not dependent on that event. Okay, and that's why the two events are independent, because the occurrence of one does not affect the probability of the occurrence of the other. Okay, 2 cards are selected from a standard deck of 52 playing cards. The first card is not replaced before the second card is selected. Find the probability of selecting a jack and then selecting a 6. Okay, so a lot of people are not actually super familiar with a deck of cards and what they're made up of. So on page 134 of your textbook, it has this little diagram. Also, you can just Google things like this and it'll show you like what makes up a deck of cards. So quick overview here. We have 4 different suits. Hearts and diamonds are red. Spades and clubs are black. And then within each suit, we have the numbers 2 to 10. And then we have Jack, Queen, King, and Ace. Now, if they ever talk about a face card, that's going to be I'm drawing a blank here. I'm pretty sure that all of these have faces on them, but it's called a face card because the card has the face, like a picture on it, rather than just a number. So there's 52 cards in a standard deck, so you end up having, what is that, 13 in each, right? Okay, so let's go through now that we know a little bit about what a deck of cards looks like and answer this question. Okay, 2 cards selected from a standard deck of 52 cards. We're pulling 2 cards, one after the other. So we're going to have 2 fractions, and we're going to multiply them together. So this fraction is the first card pull. This fraction is the second card pull, like the probability of the first and the probability of the second. The first card is not replaced before the second card is selected. Find the probability of selecting a jack and then selecting a 6. Okay, so when I go to pull the first card, my denominator needs to be how many cards I have available to me. There's 52 cards to pull from. I want to know the probability of pulling a jack. Well, there's a jack in every single suit. So there's 4 jacks. So I have a 4 out of 52 chance of pulling a jack. Okay, so that was the first pull. It's telling me that the first card is not replaced before the second one is selected. So I pull the jack out and I set it off to the side. Now for the second pull, I don't have 52 cards to pull from anymore. There's not 52 cards there anymore. There's only 51 because I took one out. And they want the probability that the second card is a 6. So we look at the 6s, just like the jacks, there were 4 of them. Now, when I pulled a jack, it didn't affect the number of 6s that were available. I still only have 4 6s available. So that's going to be 4 out of 51. Now, that's not to say that they can't give you one where it'll affect it, and we'll do some problems later where it does, but in this one, it doesn't. If I pull a jack, I still have the same number of 6s available to me. I just don't have the same number of total cards available to me. Okay. So, oh, also, little side note here, another way that you can think of this is that this is using the multiplication rule because we're doing we're doing and. So this is the probability of A and B is the probability of A times the probability of B given A. And these are dependent. These are dependent, so the probability of B given A is different from just the probability of B, right? So the probability of A times the probability of B given A. So the probability of selecting a jack, and then the probability of selecting a 6, given that I pulled a jack out of the deck and didn't replace it. Okay. So we're going to plug this into the calculator. I would say if you're if you're not super, excuse me, if you're not super comfortable with like order of operations and things like that, just put your fractions in parentheses so that your calculator doesn't calculate something different than the way that you want it to. Okay. So that's how they're getting 0.006. All right, number 15. A patient has a 59% chance of surviving bypass surgery after a heart attack. If the patient survives the surgery, then the patient has a 70% chance of making a full recovery. Find the probability that the patient survives the surgery but does not make a full recovery. Okay, I'm going to get a drink real quick. Okay, so they said patient has a 59% chance of surviving. And then if they do survive, after that, there's a 70% chance that they make a full recovery. But they want the probability that the patient survives, but then instead of making a full recovery, that they don't make a full recovery. So if 70% chance of making the full recovery, we need to find that they don't make a full recovery. So we're going back to, we talked about this a little bit before, the complement, right? So yeah, I guess I'll write it like this. 1 minus the probability of making a full recovery is the complement of that, the probability of not making a full recovery, right? So they gave us this. Probability of making a full recovery is 0.7 or 70%. So if I do 1 minus 0.7, I'm going to get 0.3. But keep in mind, this is just for this second part of it, because we still have to keep that first part in mind, right? Of just surviving the surgery itself. Okay. So what we're going to do is we're going to say, okay, we're going to do the probability that they survive times the probability that this person survives times the probability that they don't recover. Right? And that's always breaking my lead. This is our big picture here, right? This is what they're asking for. Find the probability that a patient survives surgery. Okay, the probability that they survive, but that they don't make a full recovery. So we're going to multiply these two things together, and we needed to find this because we weren't given this, right? We weren't given that they didn't recover. We were only given that they did recover. So that's why we did this. Okay, so what was the probability that they survived? It was 59%. So that's 0.59. And what's the probability that they don't recover? That's 0.3. You can, put it in parentheses if you want. So when you plug that into the calculator, it's going to be 0.177. So almost an 18% chance, 17.7% chance that if they survive the surgery that they're not going to recover. Okay. Number 16. decide if the events A and B are mutually exclusive or not mutually exclusive. A person is selected at random. A, their birthday is in the fall. B, their birthday is in October. So don't forget this terminology here, mutually exclusive events cannot both occur, right? That's what that means. If two things are mutually exclusive, they can't both happen. It's not possible. There's no overlap of the two things. They can't both be true at the same time. So the birthday's in the fall and their birthday's in October. My birthday's in October and my birthday is always in the fall. Fall encompasses all of October, right? The fall starts in what, September 22nd, and it goes until, I don't know, November something, right? So the whole of October is in the fall. So they're both existing at the same time, which means they're not mutually exclusive. Because remember, mutually exclusive means that they can't both occur. But these can. These can both occur at the same time, which is why they're not mutually exclusive. Now, if they had said their birthday's in the fall and their birthday's in May, then that would have been mutually exclusive because both of those things can't happen at the same time. Okay. Okay, number 17, table lists the smoking habits of a group of college students. If a student is chosen at random, find the probability of getting someone who is a man or a woman. Round your answer to 3 decimal places. Okay, we're going to do this the long way, and then we're going to do it the short way. Okay. So when we have that or, right, you're going to do, we're going to do the probability. Let's see, how do I want to write this? That they're a man plus the probability that they're a woman, and we don't have a field for any overlap for that. So probability that they're a man, how many people total were there? 421 total, right? That's how we read these charts, right? That's the total of everybody. And of that, how many of them were men? There were 203. Okay. All right, now we're going to find the probability that somebody is a woman. So again, our denominator is the total number of people that we had, 421. And out of those, how many of them were women? 218. Okay, and we're going to take these fractions and we're going to add them together. Right, I have a denominator of 421. If I have a common denominator, it can stay the same, and I'm going to add across the top. And when I add those two together, I'm going to get 421. And if I plug that into the calculator, it's going to give me 1. Right, so that's the long way. The short way is to say, hey, I have a survey here, and I've asked people to choose to let me know, are you a man or are you a woman? I'm giving you those two options. That's all you have to choose from. What's the probability that somebody chose option 1 or that they chose option 2? Well, that's everybody. You can only do one or the other. Those are the only options we were given, 1 or 2. So if you want the probability that it's 1 or 2, well, then that's everybody. That's everybody. So it's 1 because it's 100% of people are either this or this in this survey, right? So that's why we're getting a 1. They could have also said, if a student's chosen at random, find the probability of getting somebody who is a non-smoker, a regular smoker, or a heavy smoker. Same general idea. Either I add up 322 out of 421 plus 84 out of 421 plus 15 out of 421, and I get that it's 421 out of 421. Or I say, well, look, I only gave people 3 options. They could only choose that either they're a non-smoker, a regular smoker, or a heavy smoker. So if I'm asking you, what's the probability of getting somebody who is this or this or this? Well, it's everybody. It's 100%. It's all 421 people out of the 421 people, which is 1, right? So if you're kind of too sort of like focused and in it and not really paying attention to the big picture, you're still going to get the right answer. You're just going to spend some extra time doing it. Okay? All right, the distribution of master's degrees conferred by a university is listed in the table. Assume that a student majors in only one subject. What's probability that a randomly selected student with a master's degree majored in business, education, or engineering? Round your answer to 3 decimal places. So again, with this or, we're going to add the probabilities of each and then subtract where they might overlap, but they're saying, hey, there is no overlap. People are only majoring in one subject. So we're going to do a fraction for business, a fraction for education, and a fraction for engineering. So you'll notice here that they didn't tell us how many degrees were conferred. So we have to find the sum of the frequencies. Again, I'm not going to add that up on the calculator. I did it before. But again, if you wanted to add that up and verify it's 904, that is the denominator for every single one of these. Right? And so again, for this one, they're asking for, so we have business, we have education, and we have engineering. So the probability that a randomly selected student got their degree in business, that's 171 out of the 904. There were 171 students out of 904 students who got their the degree in business. Same process with education. That's going to be 219. Same process with engineering. That's going to be 91. So we're going to take those and we're just going to plug them into the calculator. So you can do that a few different ways. You can put them in parentheses like this. Okay, and then you get your answer. Or if you wanted to, you could say, well, they have all the same denominators, so I'm just going to add up. I know that I've got a denominator of 904, and I'm just going to add up my numerators. Okay, so that's 481. And then I want to take that and divide it by 904. And I just hit the division. I didn't have to type in 481. If you just hit divide, it's like, oh, I assume you want to divide the previous number by that. So that's a nice little shortcut. Either way, you're getting the same decimal. Okay. Again, because it's or, you add each of them up and then you would subtract where they overlap, but we have no overlap here to subtract. Okay, of the cartons produced by a company, 5% have a puncture, 8% have a smashed corner, and 0.6 have both a puncture and a smashed corner. Find the probability that a randomly selected carton has a puncture or a smashed corner. Okay, so we were literally just talking about this, where this is the probability of A or B means that you do the probability of A plus the probability of B. Then you're going to subtract where they overlap, the probability of A and B. Okay, it's the addition rule. Okay, so the probability of A, that's the puncture. What did they say the probability of a puncture was? 5%. So that's 0.05, right? 5 out of 100, 0.05, 5%. Plus the probability of B, that's a smashed corner. 8% have a smashed corner, so that's 0.08. Then we have to subtract A and B, where they overlap. So what percentage of them have both a puncture and a smashed corner? That's this 0.6%. So you want to be really careful that you don't do 0.06 because that's 6%. This is 0.6%. So this is saying not even a full 1%. It's a part of a percent. Now, if you're ever unsure when you're trying to go from percentage form to decimal form, remember all you have to do is take your decimal and move it to the left 2 places, right? When I'm here at the number 5, even though it's not written, I've got a decimal right there. So if I'm And in percentage form, to go to decimal form, I take my decimal point and I move it to the left 2 places. So now it's going to be here, which means I need a 0 in this place here. Or you could say divide it by 100, right? 5%, that's 5 divided by or out of 100 is 0.05. So whether you're doing it by hand or plugging it into the calculator, if I have 0.6%, that's 0.6 out of 100 is 0.006. So just, again, you don't want to get a question wrong because you accidentally did 0.06 instead of 0.006. Okay. So we plug this into the calculator and we have 0.05 plus 0.08, excuse me, minus 0.006, and we get 0.124. Now, I've just been talking about how to go from percentage to decimal because it's important that you know that, but actually you'll notice here that they actually just want you to give the answer as a percentage, okay? So what you could have done was you could have said 5% plus 8% minus 0.6%. And when you get your answer, it's going to already be in percentage form. So 5 plus 8 minus 0.6 gives you 12.4. So for this problem, you do it this way, you're going to get your answer. It's already in the right format, but you want to make sure that you're comfortable doing it this way because there's going to be plenty of problems where you have to give them the decimal form, not the percentage form. Okay. All right. Number 20, a card is selected at random from a standard deck of 52 playing cards. Again, I've given the little diagram here of what makes up a standard deck. Find the probability of each event. So we're doing this 3 times. All right, randomly selecting a heart or an ace. All right, so I'm going to have a fraction for a heart plus a fraction for an ace. And then because this is or, I would then subtract the probability that it's both a heart and an ace. Okay, so I'm going to subtract, and this is going to be the probability of a heart and an ace. So this is, I guess let me write it up here. Probability of a heart, probability of an ace, probability of an ace of hearts. Okay, because that is the or, is you add them up and subtract where they overlap. Now, they're not doing any of this like, oh, I'm pulling a card and then not putting it back, right? So our denominators here are going to stay the same. There's 52 cards in a deck. That's what I have available to me. Okay, so how many hearts do we have? Hearts are one of the suits. It makes up a quarter of the deck. So 52 divided by 4, there's 13 cards in each of these in each of these suits. Okay, the probability that it is an ace. So, excuse me, I have 4 aces, one of each suit. So there's 4 out of 52. But how many ace of hearts are there? There's just the one. There's only one ace of hearts. So that's 1. So again, however you plug this into the calculator, that's easiest for you. I would just plug it in all at once and make sure that I have my parentheses on. And I get my decimal. Again, if you round that to 3 decimal places, as they say to, you get 0.308. Okay, the next thing is randomly selecting a black suit or a 7. So again, or, so I'm going to do the probability of a black suit plus the probability of a 7 minus the probability of a black suit that is a 7. So I didn't leave myself a lot of room for that. But so this is the probability of a black card, separate from this. This is the probability of a 7, and this is going to be the probability of a black 7. Okay, All right, so the probability of a black card. Well, half the deck is black. So half of 52 is going to be 26. Oh, also, again, 52 cards in a deck. That's our denominator for all of these. Okay, half the deck is black, so 26 out of 52 is the probability that it's black. Probability of a 7. So how many 7s are there? There's 4 7s. So I have a 4 out of 52 chance of getting a 7. And then what's the probability that they're both black and a 7? Well, I have 2 black 7s. I have a spade and a club. Both of those are black and 7, so I have 2 black 7s. So again, I'm just going to plug this into the calculator a slightly different way, just, if you're doing it a different way. I know that my denominator is going to be 52. I'm going to say 26 plus 4 minus 2. That's my numerator. And then I'm going to take that and divide it by 52 and round that to 3 decimal places, right? Just to kind of show you some variety in how you can plug these in. Okay. And then for part C, randomly selecting a 5 or a face card. So, oh, you know what? Yeah, you know how I was hesitant before when I was talking about the face cards? Face cards don't include aces because aces don't have faces on them. So yeah, just the king, queen, and jack have faces. Okay, so let's do this one. So again, we have something plus something minus where they overlap because we have or. So this is going to be the probability of a 5 plus the probability of a face card minus the probability of a 5 that is a face card. Well, wait a minute. None of the 5s are face cards. There is no overlap, so we're not going to have to subtract anything. Or if we wanted to, we could, but it's going to be 0. All right, so the probability of 5. So again, I've got denominators of 52. Probability that I have a 5. There's 4 of those cards. Okay. The probability that it's a face card. So again, just the king, queen, and jack are face cards. Aces do not have faces on them. That rhymes. So we have 3, 6, 9, 12 face cards, 3 of each suit. Okay. And then if we wanted to have a fraction here, we could say this would be a denominator of 52, but how many 5s are face cards or the overlap of 5s and face cards? Well, that's 0 out of 52. So if I have 4 out of 52 plus 12 out of 52, that gives me this number, which when I round is going to get us the point, or the, 0.308. Okay. All right, number 21. Decide if the situation involves permutations, combinations, or neither, and explain your reasoning. Okay, so quick vocab reminder, sorry, permutations. The order matters. Order matters. Combinations. The order doesn't matter. Order, it's an E, doesn't matter. Which is why I hate when you buy a lock for your bike that it's called a combination lock, because no, it isn't. It's not a combination, it's a permutation. Because the order that you put those numbers in absolutely matters. And with combinations, the order doesn't matter. Okay, so we're deciding if this involves one or the other or neither. Okay, the number of ways 11 people can line up in a row for concert tickets. Okay, so if there's a chance that the concert tickets are going to run out, it matters if I'm the first person in line or if I'm the 11th person in line. If they only have 10 tickets left, it matters, right? Order matters here. So yeah, it's a permutation because the order matters, because if I'm first, I'm in a different situation than if I'm 11th, depending on how many tickets are available, right? So permutation order matters, combination order doesn't matter. All right, 22, determine whether the following problem involves permutation or combination and explain. How many different 7-letter passwords, we're looking at a password, can be formed from the following letters if no repetition of letters is allowed? Well, whether repetition is allowed or not, a password, the order absolutely matters. Order absolutely matters on a password. So that makes it a permutation, right? If you have a bunch of letters and they're in a completely different order than the last time you plugged it in, it's going to tell you your password's wrong, right? Order matters in a password, order matters in permutations. So that's why this is a permutation. It does matter. Okay. All right, you have 9 different video games. How many different ways can you arrange the games side by side on a shelf? All right, so we're going to do this 2 different ways. So the first way is kind of similar to how we were doing the first couple of problems. I've got 9 different video games. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to fill each of these in with how many different ways or how many different options I have for that, right? Like we did it at the first like 2 problems. So for the first slot on my shelf, I can choose any of the 9 video games, right? But once I choose that video game, I don't have 9 video games to choose from anymore. I only have 8 for the second slot. And once I choose that second one, now I only have 7 left. And then I only have 6, and then I only have 5 and 4 and 3 and 2. And for the last slot, I only got 1 left. That's the only one that can go there. Okay, so that's the long way. The shortcut of this is you do 9 factorial. Okay, so that exclamation mark is the factorial symbol. Okay, and in your calculator, if you do this the long way, you're plugging in 9, 8, 7, 6, 5, 4, 3, 2, 1. If you don't do the times 1, that's fine because anything times 1 is itself, but you're getting this big number. Or you can use the factorial button. Okay, so what you're going to do is you're going to do 9, and then you're going to go to, I think it's math. Here, let me move this up a little bit more. So math, and if you arrow over to number, N-U-M, then, oh, no, I'm sorry, probability, because we're talking about probability. There it is, number 4 is the exclamation mark, the factorial, and you get the exact same thing. So again, you're going to hit the, here, I'm going to write this here, you're going to hit the math button, right? And then you're going to arrow over to probability, P-R-O-B. You can also hit the left arrow and it'll like circle back around to the menus on the right, okay? So it's like fewer clicks to do that. And then you can either arrow down to the number 4, or if you're back here at the top, if you just press 4, it'll select it. So, okay, math, probability, and then 4, which is exclamation mark. Okay, so that's where the exclamation mark is, and either way, you're getting the same answer, which is 362,880. Also, if you're in a menu and you want to get out of it, you want to quit the menu. You can see that quit is above mode, so it's kind of like the shift button where you have to do second and then the quit button, and it quits. Oh, I didn't mean to tell it to do that. Okay. Number 24, there are 43 runners in a race. How many ways can the runners finish first, second, and third? Okay, so again, we're going to do this a couple different ways. So we can say, all right, well, I have first, second, and third place. Okay. And we say, well, how many options do I have for first place, second place, and then third place? So there's 43 runners in a race. So any of them could be first. But once somebody is first, there's not 43 options for second place. There's only 42 options because somebody already got first. So they can't be both first and second. Okay, it's fine. And then we continue that pattern for third place. Somebody got first, somebody got second. I no longer have 42 people to choose from. I only have 41 people to choose from. Okay. Or we could do in the calculator, we're going to do 43, choose 3, where the order matters. Because remember, this is a permutation because order matters, right? I care if I'm first or second or third. Okay, I'm not going to use the exclamation mark because that means something specific. So in the calculator, it's going to be in that same menu. Okay, we're going to hit Math. My LEDs are giving me issues. Okay, there we go. All right, you're going to hit Math, and then you're going to arrow over to Probability. Okay, and then number 2 and number 3, we have NPR and NCR. This is for permutations, this is for combinations. Okay, so for this one, we're going to select number 2, which is NPR. Not to be confused with National Public Radio. Okay, NPR. Now, if you already put a number in, it's going to assume that the number that you already put in was supposed to be the number on the left here. Okay, but let's go ahead and plug in our 43, and then we're going to arrow over to the other part, and we're going to plug in our 3, and then it gives us our answer. Okay. Oh, I never actually plugged this into the calculator. So if you do it this way, you do 43 times 42 times 41, and look at that, we get the same number. And then the other option is to use the formula. Okay, so you guys, again, they're not expecting you, unless they say otherwise, they're not expecting you to do it by hand with the formula. They're expecting that you know this tool and that you use this tool in the calculator. They still need you to know that a formula exists though, right? The calculator doesn't just like magically do this, it's using a formula behind the scenes, right? So it is important that you guys are aware of this formula, especially if you have like an instructor who wants you to like show them the steps that you're using when you're doing the formula. Okay, so if you have, oops. So if you have NPR, this is your formula. Okay, it's n factorial over n minus r factorial. Okay, so in our case, we have our n is 43, our r is 3. Because remember, n is the total number of people you have to choose from, or things you have to choose from, and 3 is how many of them you're choosing. Okay, so in our case, we have 43 factorial, that's our n, over n minus r, well, that's 43 minus 3 factorial. Okay, so again, we can plug this into the calculator. Remember, the factorial symbol is in that same math probability menu. Okay, so I'm going to say 43 factorial divided by 43 minus 3 factorial. And conveniently, we get the exact same number, right? So you can do it either this way, or this way. This is going to be the way that you're going to do it if they don't specify that they want you to do it another way, because it's faster. Well, I guess it depends. Some of you, this might be faster to plug in. I guess that's a fewer number of clicks in the calculator. But they're not going to expect you to do it this way. It's important that you know that there's this formula, but even though you know that there's a formula, they're fine with you just doing that. If you're taking this class in person, your instructor might have some different preferences there. Like they might have a question on the test where they're like, hey, you need to use this formula. Show me that you're using the formula. But generally the online classes, you're just going to be plugging this into your calculator. Okay. All right. 25, there are 12 finalists in a singing competition. The top 6 singers receive prizes. How many ways can the singers finish first through 6th? So again, order matters here, right? So this is going to be a permutation. The number of singers I have is 12. The number of them that I'm choosing is 6. So this is 12p6. Or you can think of it as 1, 2, 3, 4, 5, 6. And I'm going to do 12 people times 11 people times 10 people times 9 people times 8 people times 7 people. Right? You can do it either way. But whichever way you do it, and here I'm going to type the 12 in first, and then I'm going to go math, and then, whoops, 12p6. Either way you do it, you're getting 665,280, right? Really big numbers. But also I could do 12 times 11 times 10 times 9 times 8 times 7. I feel like that's more clicks. Or you could do it using the formula. But either way, you're going to get that same answer. Okay, number 26. In order to conduct an experiment, 4 subjects are randomly selected from a group of 42 subjects. How many different groups of 4 subjects are possible? Okay, so I'm looking at a group of subjects in an experiment. I don't care what order they are within my group. I just need to pick 4 people. So this is going to be a combination, not a permutation, because the order doesn't matter. Right? Order doesn't matter. So how many people do we have to choose from? 42. How many of them are in this randomly selected group? 4. So I'm going to do 42 math. This is, we're going to now do C, right? And CR and 4. And that's how they're getting that. Or you could go straight to that menu and then you'll have an opportunity to put in the 42 and then you just arrow over to the 4. Okay, you're still getting the same thing either time. Okay, and then class has 27 students. And how many different ways can 6 students form a group for an activity? Assume the order of the students is not important. Okay, if the order is not important, it's a combination. Okay, there's 27 students. How many of them am I choosing? Choosing 6 of them. So 12, choose 6. Oops. It's not 12, it's 27. Where did I get 12 from? 27. Choose 6. There we go. That makes more sense. I don't know where I was getting 12. Okay. And then last question. A certain lottery has 25 numbers. How many different ways can 4 of the numbers be selected? Assume that the order of selection is not important. Not important. This is combination. Okay, we've got 25 numbers and we're choosing 4 of them. So again, we're just plugging it into the calculator. Let me make sure that I have the right number of numbers. And that's how they're getting that number. Okay. All right. So I'm going to email the recording of this out to you guys. Hopefully this helps. Don't hesitate to come into the Academic Support Center at whatever campus you're closest to. I'll be including the link to the ASC's homepage so you can see when your particular ASC is open and who is working there. We pretty much have people who can help with statistics on every campus. If you can't get to a physical campus, you can still use our chat feature, which is on our website, where from 8 a.m. to 7:30 p.m. Monday through Thursday and 8 a.m. to 5 p.m. on Fridays, you can just hop online and get help. And, you know, depending on the type of problem, we can set up like a video call like this. It doesn't take too long to just switch over to a video call rather than a chat. And also don't forget that on Saturdays, we do have the Academic Support Center that's located inside of the library. So the one in Building 115 on the Daytona campus, that is open from 8 a.m. to 4 p.m. on on Saturdays. And we do have people there that can help with statistics. So that's always an option as well. All right. Well, again, I hope this helps and good luck.